about parameterized surfaces. Enough to do this section. We'll go more in depth with them later this semester. We'll plot them, spend more time with them. But we'll cover them enough so that we can do surface area. So basically what's going on is we have a 3D surface, right? Think of a sphere. Well, we want to calculate the surface area of that sphere. We have a formula for doing that for a sphere. We don't for generalized functions, but we can use an integral to do so, all right? And so what I'm going to do is I'm actually going to start with a parameterized surface, even though we're not that familiar with them, because it's really easy to see how surface area works with a parameterized surface. Then we can convert it for a function, which is you saw two formulas coming into today. I'm going to show you where they both come from. All right. So basically what's happening is we've a parameterized surface. We looked at parameterized curves, right? Remember when we did the helix, the conical helix, all that stuff? Our parameterization was of one variable. A parameterized surface is going to be of two variables. That's the only difference. And it's the same basic idea. Having that second variable creates a surface. Again, we're going to go more into depth why in module 15. But here's what here's our takeaway. So what's happening is this vector valued function, what it's doing is it's taking something in the UV space and mapping it onto the surface. So say taking something in our XY plane and mapping it onto some surface out in 3D space. All right. So what's happening? I want to give you just a little bit because this is going to show you where the formulas you saw come from. So let's say here we've got our region R. Let's call this U, this V. Well, then what that vector valued function does is it takes R and it maps it onto some surface in the XY plane. Or sorry, some surface in 3 space. All right, so actually we can even throw in our 3D. So that's what R is doing, that vector valued function. It's taking ordered pairs and mapping them onto a surface. So it creates the surface for us. It's a little bit, it works a little bit differently than having some function z equals x squared plus y squared. All right, this is a little bit different way of doing it. We can get a lot of the same functions, and I'll show you that here in a second. But what we're trying to do is get the surface area of S. All right, well, the idea is nothing new. What we do is we take our region R and we break it up into a bunch of, except in this particular case, they're going to be delta V's and delta U's just because of the letters I happen to use. But same idea, right? Well, those correspond to certain regions on the surface. Now, these regions, because the surface may not be rectangular, actually, our region doesn't have to be rectangular, we're simplifying it. But, you know, this block may correspond to this block, right? This block to this block. So what we do is we break that up into a bunch of little deltas. Okay, so what I want to focus on is just one of these squares. So we zoom in on one square here, and that thing is getting transformed via R into one of these, something like that, okay? Now, what's happening is we have, this is happening at some UV point, right? So this is some U comma V. So this would be U plus delta U comma V. This would be U comma V plus delta V. And this would be U plus delta U comma V plus delta V. And this is not something I would want you to take notes on. I just want you to see where the formula comes from. And this is basically our introduction to parameterized surfaces. So we'll probably either skip this part or just briefly talk about it when we actually get to that section. Well, each of these corresponds to something over here, right? So now they're getting put into R. So this would be R of U comma V plus delta V. I won't do all of these just because I don't want to bore you with it, but you know, one of those for each of the corners there, right? We're getting that mapping. So again, just think of R as it takes the points in the XY plane, maps them onto the surface. Creates the, that's what R does. It creates the surface for our ordered pairs, our inputs. Now, what we need to do is, what we're trying to do is find the area, actually, so R U plus delta U, comma, V plus delta V, R of U plus, yes, U plus delta U, comma, V, and R of U, comma, V. Okay, so what we're trying to do is calculate surface area. Let's go back to where we wanted the area of this whole surface, right? That's defined by our vector value function. So what we're going to do is start by thinking about the area of this guy. Well, what we do is we look at the length of one side. What we're going to do is we're going to make delta U and delta V so small that eventually we can assume these sides are straight. Now, we don't necessarily get a rectangle, but we would get a parallelogram. And that's going to be key to where the formula comes from. So one side of this, let's do this side here. The length of that side is R of U plus delta U, comma V, minus R of U, comma V. Not a big deal, right? We're just finding the length of that side, end minus start. Okay, well, now I'm going to do something to this. I'm going to divide by delta U, but I'm also going to multiply by delta U. So I don't change what I have. Now, here's the thing about this part right here. If I take the limit as delta U goes to 0, I have the definition of a partial derivative. This is the partial derivative of R with respect to U. So what this is basically approximately R with respect to U, the partial with respect to U. Right now it's on, well, delta U is going to 0. So du. Okay. That gives us one side of the parallelogram. Very similarly, this side of the parallelogram would be approximated by R sub V. Now we're going to go back to cross products. This is a while ago, but I don't know if you remember. One of the interpretations of cross product is when we cross product two vectors, it gives the area of the parallelogram created by those two vectors. So the area of this guy is going to be approximated by, kind of ran out of room, but the area of this guy is going to be approximated by RU cross RV, and then DU DV. That's just for this one guy, and we're going to take the magnitude of that because the magnitude is the area. We don't want a vector. So that takes care of one of these squares. We just now need to add up over the whole region. All right, that is where this formula comes from. These two, the double integral sums up over all of those parallelograms. The cross product does the area of each individual parallelogram. Okay, that what I just did is not something you have to do. To be honest, it's not even something you really have to understand. I just wanted to give you some idea of where this came from because all of a sudden there was a video in the lesson about parameterized surfaces and we haven't seen those before. All we need to know about parameterized surfaces for right now is that what they do is they take something in the XY plane. It's a vector valued function, which we have seen. and maps it onto the surface. So it creates a surface. All right. Now we have the formula. Let's see how this works. Oops. Okay. So a cone of height 1, and that has that's at a 45-degree angle. So its base radius would also be 1. For right now, you are not expected to come up with parameterizations. Like I said, that's going to be in the next chapter. It's a couple weeks away. You'll be given any parameterizations if you're asked to find the surface area, like in the homework or anything. Okay, so don't worry about that. So right here, I got the parameterization. Now here's what's really cool about this. All right, let me bring over CalcPlot 3D. Okay, so if you want to do a parameterized surface, right there, parametric surface. Now, by default, this uses U and V instead of theta and R, like I had in my parameterization. But let's use U for the radius. So we're going to have U times cosine of V. We'll have U times sine of V. So U is the radius, V is theta, and U. All right, that's our parameterization. We said it was going to have a radius of 1, and then 0 to 2 pi is what makes it go all the way around. And there is our cone. We can see from straight down, it has a radius of 1. And it's at a 45-degree angle, and it has a height of 1. Here's why this is so nice. If you can create the parameterization, these are going to be the limits on your integral. Let me say that again. The reason CalcPlot 3D is going to be really useful on some of these, when we get to parameterizations, what you need here to create your surface, those are also going to be your limits on your integral. So let's talk about setting this one up. Let's go ahead and use this version. Let's use U and V. So our parameterized surface is U cosine V, U sine V, U, and U goes from 0 to 1, V goes from 0 to 2. Everybody okay with that? And we can see it, right? That's what's so nice about this. All right. So this is our R. This is our position vector. So we need both the partials. You guys should be good at partials by now. So R with respect to U. Well, we're taking the derivative with respect to U means that V is our constant. So cosine V, sine V, 1, right? Now, if we do it with respect to V, we get, oops, sorry, I was doing it off the R sub U. Got to do it off the original. All right. Constant, now we're taking the derivative of cosine, which is negative sine. So negative U sine V, U cosine V, 0. All right. All I'm doing is partials. You guys have had a lot of practice at that at this point. All right, next thing we need, is the cross product of these two. Again, something we've done before. For time's sake, I'm just going to put it up there because there's other things I want to get to today. I don't want to have time for you guys to do stuff too. But the cross product, negative U cosine V, negative U sine V, U. Okay. And like we've talked about before, when you're working on homework, feel free to use Wolfram Alpha to help you out with the cross product. Don't kill yourself on it, okay? It's really easy to make a mistake, and I don't want you to get stuck on one problem because you had a sign error in your cross product. Yes, you need to be able to know how to do it by hand for the exam, but that's just following a formula, right? This is, I don't want you to get crushed on some of these and frustrate yourself. Okay, now we're back to the formula, which I no longer have up. So let me bring back up the formula so you guys can see it. We'll come back to Calculate 3D here in a little bit. So we need the magnitude. The magnitude is going to be our integrand, okay? Here's the thing. Once you have this, everything else is 100% procedural. Partial, procedural, partial, procedural, cross product, procedural. The magnitude of the cross product, procedural, right? It's going to be square root. I'm going to square these all at once, but all these terms are getting squared and added together. So I'm going to end up with u squared cosine squared v plus u squared sine squared v plus u squared. Check this part out right here. I got a cosine squared plus a sine squared. So we're going to have u squared plus u squared. You got it. So square root of 2u squared. And we can actually pull out the u times rad 2. So after all of that, that is our integrand. These are our limits. So if we're looking for the surface area, let's call it A. We have the double integral. We can do either first because these are constants, 0 to 1, 0 to 2 pi of u times square root of 2. You can pull out the square root of 2. It's a constant. du dv. Again, I'm more interested in setup than calculating. We spent time on calculating. But I do want to tell you that this comes out to pi times the square root of 2. And the reason is because this one is actually on the worksheet. We've already done it. So you've seen this one, but there's a part B on the worksheet. Maybe this is part B. I might be getting those backwards, where you have to do it as a function. And that's the other thing I want to show you in Calculate 3D. The other way to get a cone is as a function. So function z equals, and that function is square root of, we've seen this one before, x squared plus y squared. And I know it's a little hard to see because since it's a function, it's putting it everywhere. But if we limit the z, so we make the z stop at 1, we get the exact same cone. So one of the ones you guys might want to try when you're working problems later is the one for z equals square root of x squared plus y squared. That's all the parameter. The parameterization is a vector value function that gives us the surface. What we're going to see, just like with parameterized curves, we could all of a sudden create a helix. We couldn't do that before. With parameterized surfaces, there's going to be things we can create that we couldn't do as a function. Like I said, we're going to get into that in the next module, but we'll be able to do like the Mobius strip and things like that. Okay. Questions about this first example? Like I said, we're done with this part. I just wanted to give you an idea of where that formula came from. Yeah. Now, here's one thing I do want to point out. This parameterized surface was done in terms of cosine and sine. Okay. But one thing I did not need to do was put an extra u, or if I had left it in terms of r and theta, I didn't need to put an extra r in the integrand, because this was not taking something in rectangular and converting it to polar. Okay. And I'm going to show you the difference in not the next example, but the example after it. When and it's something I want you to be just aware of, because like this, originally I gave this parameterization in terms of r and theta, and we are doing the parameterization in polar, but it's already in polar. We didn't convert to polar to do it, so we didn't need the r as part of the dA. Right? So, like I said, once we have the parameterization, it's literally just following steps, right? It is plug and play. Yeah, there's places to make mistakes, but if we don't make any math errors, those aren't bad to do. Okay, if there's no questions about that one, let me show you why I like doing that first. Because here's the other, this is going to give way to the other formula. So we just saw one formula, right? That's going to be one formula you're responsible for. That's the surface area for a parameterized surface. This is going to give the other way of finding surface area if our function is given as z equals f of xy. So this would be the formula you would use for doing the other version of a cone, right? The square root of x squared plus y squared. So what we do is we start off treating it like a parameterized surface, but we're just going to call z f of xy. So we find the partials just like we did over there. Remember what the next step was? The next step was to find the cross product, then find the magnitude of the cross product. So take the cross product and then take its magnitude, and you get this, which should look familiar from the videos. This is the integrand when you have a function in terms of x and y. And there is the other formula. Now, here's where things are going to be a little bit different. With parameterized surfaces, our limits are the same limits that create the surface for the parameterization. Now, what we need to do to get our limits is figure out what our region looks like in the XY plane. So I'm going to do that with this example here. This, again, is going to be another setup. I'm not going to calculate it because, again, we've spent time calculating integrals. Right now, I want to focus on setting them up. So here's how you deal with something like this. So we want the surface area of the plane that's in the first octave. We have to be given some kind of limits on it because otherwise the plane's infinite. So here's one way of handling this. And this is, so this will be our second example. Well, if we're just doing the first octave, then all we need are where it hits the axes. Okay, so it's hitting this z-axis at 0, 0, 6, right? Let's see, we're going to hit the x-axis at 2, 0, 0, 2, 0, 0. And we're going to hit the y-axis at 0, 3, 0. Remember, if we're looking for intercepts, you set two of your variables to 0 and solve for the third. So for instance, how did I find the x? Well, 0, 0. So I end up with 6 minus 3x equals 0, x equals 2. Because we're only looking in the first octave. So this is the piece of the plane that we're looking for the surface area of. Now, let's start off with the easy part, and then we'll talk about the more fun part, where there's more to do. Our integrand is pretty easy. What's f sub x for this function? Or negative. Everybody okay with -3? All right, f sub y. So our integrand is -3 squared plus -2 squared plus 1. Right? So it's right back into that very, very procedural. You know your function, you find your partials. Now, they may not always be constants. This part can get really messy depending on this function. If it's really messy, use Wolfram alpha to solve your integral. Okay? You don't have to solve the messiest of integrals by hand. Exactly. Now, here's where your work is going to come in, though. We have to figure out our region of integration. And that's going to be what I call the shadow region in the XY plane. And I call it shadow region because right now this thing is opening downwards, so our region is right here. But if this had been opening upwards, we would think of a light coming straight down and what that shadow would look like in the XY plane. That's going to be something we'll talk about even more next week on triple integrals, this idea of a shadow region. So we need to think about what this thing looks like in the XY plane. A couple different ways we can do it, but we know that it hits at 2, 0 and 0, 3. So one option is just to find the linear function between those. The other option is we're in the XY plane, so we're where z equals 0. So the equation of this line is 6 minus 3x minus 2y equals 0. And then we can solve this for x or y, depending on which one you want to do first. So let's go ahead and solve it for y. So we have 2y equals 6 minus 3x. Divide everything by 2. And we end up with y equals negative 3/2 x plus 6. Or, excuse me, not 6, 3. Okay, so the equation of this line in terms of y equals 3 minus 3/2 x. So the way I have it set up, I'm going to do vertical first, right? Because I've got it in terms of y. You find the inverse, you can do horizontal first. This triangle, we can do either direction first. Because we're back into doing the region for these things is the same as doing the region for double integrals. The same basic idea. It's just now we have something we're integrating over, and that comes from the partials. But as far as finding the region, exact same thing you were doing in double integrals. So I'll go 0 up to the line. So 0 up to 3 minus 3/2 x. So I'm doing y first. And x goes from 0 to 2. And that will give me the surface area that we're looking for. Questions about that one? And I'm going to be leaving these up here. That's why I'm using the whole board today. So you can reference these examples as you're working on the worksheet. That's why we cut out the other side. So, all right, one last example. Find the surface area of the function xy between two cylinders. And what does this look like? Let's see, let's get rid of this guy and this guy. And put in, okay, there's the surface xy. There's the there's the first cylinder, there's the smaller cylinder, there's the bigger cylinder. So you can see that's the surface that we're trying to get between those two cylinders, right? Okay. So now we got a visual of what's going on. Before we even start this problem, is this going to be easier to do in rectangular or polar? Definitely polar, right? Once we have to deal with those cylinders, doing it in polar makes our life a lot easier, because if we think about how we're going to integrate, right, we're going from this cylinder to this cylinder. So R is just going to go from 1 to 2. And theta is just going to go from 0 to 2 pi. So all of a sudden our limits get really easy. Okay, so let's talk about setting this thing up. We already know what the limits are. Sometimes the limits are the hardest part, right? The problem we just did, the limits were the hardest part on it. We already know the limits. So now all we got to do is set this thing up. So this is going to be really cool. So Z, where did I call it? Did I call it Z? Z equals XY. Here's the cool thing. I can do the partials before I change it to polar, because the partials are easy to do here. Oops. What's Z what's the partial of Z with respect to X? What's the partial of Z with respect to Y? And now we'll put it in our polar transformations. Okay. Now remember, let's see, I don't have it. I don't have the formula. So let me put the formula back up. Remember the formula. The formula stays the same. So we have the double integral of the square root of r sine theta squared plus r cosine theta squared plus 1. We can do either, we can go r first or theta first. Probably going to be easier to go r first. So 1 to 2, 0 to 2 pi. We need the limits. So we know we're going dr d theta, but because now we are changing it to polar, now we need the r dr d theta. R dr d theta. And I ran out of it. Okay, I know it's hard to read, especially for you guys at home. That's a dr d theta. Everybody okay with that? Sorry, it's such a mess. All right, that's it. Like Wolfram Alpha can finish this thing off for us now if we want, but look at what's going to happen again. We're going to have an r squared sine squared and an r squared cosine squared. That r is not under the radical, which is actually going to be a good thing for us. Sine squared plus cosine squared is, oh yes. Oh, you're the same one. So this becomes just r squared, right? This whole thing here is just r squared. So last step that I'm going to do. So we're going to end up with square root of r squared plus 1, r dr d theta. And thanks to that little r right there, this is set up perfectly for a u sub, right? We'll let u be r squared plus 1. That'll allow us to do our u sub. That'll take care of the first integral. The second integral will be really easy because it's basically just going to be multiplying by 2 pi. So we have something we can finish off from here. All right. Again, I wanted to focus more on setup than calculating. And for those of you guys who do need it, make sure you practice u sub. It does come up a lot, as you're probably noticing in the last couple sections. Now, again, the reason I wanted to do this one is the contrast. Notice what happened here in the blue on the right versus the blue on the left. In the blue on the left, we were doing a parameterized surface that was already in polar. So we did not have to put in the r into the integrand, right? Parameterization is already in polar. You do not have to add an extra r in. In this case, our function, we were given a function in terms of x, y, but we knew it'd be easier to do in polar. So we converted, so we needed to put in the extra r. So that's what you want to look for now, because it will get a little tricky because before we were just always converting. Now we might actually be given a parameterization that's already in polar, and you don't want to just get into this auto, oh, it's polar, I'm going to add in an r. If it's a parameterized surface, then it'll be obvious. This is not going to be something that's, that's not obvious. You will know because it's given as a parameterized surface. It's given as a vector value function, and you're specifically using that cross product formula instead. In this case, we weren't using the cross product formula. We were using the formula for a function.